Myself, Mrs. Afroz Pathan. I am Assistant Professor in Department of Pharmaceutical Chemistry and Analysis, School of Pharmaceutical Sciences, Vistas. My topic is carboxylic acids and acid constant. Carboxylic acids. Carboxylic acids are a group of class of organic compounds in which the carbon is bonded to an oxygen atom by a double bond and to an hydroxyl group by a single bond. The most important property is its acidity, and that is the reason why it has been named as an acid. According to Lewis' theory, an acid is a compound that donates a hydrogen ion, means H plus or proton, to another compound. Carboxylic acid do this much more readily than most of the other class of organic compounds, so they are said to be stronger acids. But even though they are much more weaker acids than most important mineral acids like sulfuric acid, nitric acid, and hydrochloric acids. The reason for this enhanced acidity of this group of compounds can be best demonstrated by comparison of their acidity with that of alcohols, both of which contain an hydroxyl group. Alcohols are neutral compounds in aqueous solution. When alcohol donates its proton, it will become negative ion and it called as alkoxide ion as shown in the figure. Whereas carboxylic acid, if it donates proton, it becomes a negatively charged ion called as carboxylate anion as shown in the figure. A carboxylate anion is much more stable than corresponding alkoxide ion. The reason behind this is due to existence of resonance structures of carboxylate anion, which helps to disperse its negative charge. So, as only one structure can be drawn for alkoxide ion, but whereas two structures can be drawn from carboxylate anion, making the carboxylate ion more stable than alkoxide ion. And if you see in the reaction, the equilibrium shifts towards the left hand side, making more stable carboxylate ion much easy to form and produces H plus ion, so behaving it as an more stronger acids. So in the reaction, you can clearly see that two resonance structures has been written for carboxylate anion with a resonance hybrid. So in both the cases, the distribution of negative charge between both the oxygens are same. Acid constant. An acid dissociation constant is also called as Ka, and it is also known as acid ionization constant or acidity constant. The definition includes it is a quantitative measure of strength of an acid in a solution. It is an equilibrium constant for a chemical reaction, also known as dissociation constant in contrast in acid-base reactions. Acid constant can be derived by Henderson-Hasselbalch equation. So if you see in a reaction Ha, which behaves as an acid when dissolves in water, it forms as dissociated ions, hydronium ion and carboxylate ion. So when you write the K equilibrium, it is nothing but the concentrations on the left hand side divided by the concentrations on right hand side. So the concentration of water is unchanged. If you shift that to K equilibrium, it will become acid constant. So acid constant is nothing but concentration of dissociated ions divided by concentration of undissociated acid. So Ka is specific for specific carboxylic acids. The Ka can be changed into pKa by taking its negative logarithm. And the similar way we can explain for carboxylic acids also. Carboxylic acids, when dissolved in water, it will form carboxylate anion. So to define Ka, it is nothing but concentrations of dissociated ions, that is carboxylate ion and hydronium ion, divided by concentration of undissociated acid, that is your carboxylate. Ka is characteristic and it is specific for each compound. Alcohols are weaker acids than carboxylic acids. Carboxylic acids are weaker acids and it ranges from 10 power minus 4 to 10 power minus 5 in Ka values, and if you change it into pK, it will range from 4 to 5. So if you take an example of acetic acid, if dissolves in water, its dissociation constant or Ka will be 1.74 into 10 power minus 5, and changing that into pK, it will become 4.76. As the Ka value increases, acid strength increases, and as the pK value decreases, acid strength increases. You can clearly see the table column where substitution of chlorine one by one will cause a decrease in pK value and thereby increases in the acid strength. Stability of carboxylate anion. We know that an equilibrium favors the thermodynamically more stable side, and the magnitude of equilibrium constant reflects the energy difference between the components of each side. In an acid-base equilibrium, the equilibrium always favors carboxylate anion. Both the carboxylic group and the carboxylate anion are stabilized by resonance. In carboxylic acid resonance structure, the charge separation is there, so it is less stable. But whereas stabilization of anion is much greater than that of the neutral acid, which is shown in the following diagram. In carboxylate anion, the contributing structures have equal weight in the hybrid, and the CO bonds are of equal length between a double bond and also a single bond. This stabilization leads to markedly increasing the STT by dissociating and existing as more stable carboxylate anion. Effect of substance on STT. The STT of carboxylic acids further depends on nature of the substituent like alkyl or aryl group attached to carboxyl group. An electron withdrawing group ensures effective delocalization of negative charge through resonance or inductive effect. Thus, electron withdrawing group increases the stability of conjugate base formed and hence STT of carboxylic acid. On the other hand, electron donating groups destabilizes the conjugate base formed and hence decreases the STT of carboxylic acids. So a general trend can be seen like CF3COOH is having more STT than CCl3COOH. So if you see here, the withdrawing effect of fluorine is much greater than that of chlorine. So 3-fluorine if present beside 2-carboxylic acid, generally its pKa will be very less and behaving it as a more stronger acid when compared to trichloroacetic acid. If the number of electron withdrawing groups like chlorine increases, then also STT increases. You can clearly see here acetic acid is weaker acid when compared to chloroacetic acid. And if instead of 1 chlorine, if 2 chlorines or 3 chlorines has been substituted within the same moiety, the pKa has drastically decreased and acid strength increases. On the other hand, the STT decreases as the halogen atom moves away from COOH group due to less inductive effect and to stabilize the carboxylate anion. In aromatic carboxylic acids, due to resonance effect, phenyl or vinyl groups increase the STT of carboxylic acid in spite of decreasing the STT due to induction effect. This is because the carboxylate anion carries a negative charge which can be delocalized by benzene ring. Thereby, stabilization of carboxylate ion takes place and it can produce H plus ion more readily and expect its STT. These are the references for preparing my PPT. Thank you, one and all.